Okay, so let's get started. Last time, so I forgot once again last time to repeat to the virtual audience any of the in-person questions, because when I watched the video, you guys couldn't hear the question. So I'm going to try to remember, if someone from in here asked a question, I have to repeat the question. Hopefully you were able to tell what the question was from my answer. So last time we stated and proved the Gauss lemma, one of the things we did. I'll remind you what the Gauss lemma says in a few minutes after I give some definitions, which will maybe hopefully make the Gauss lemma a little more transparent. Today is going to be a very technical lecture, a bit like last time, but even more so. We're going to prove that geodesics are locally length minimizing, that if you had a minimizing curve, it must be a geodesic. And then we're going to prove that every point has what's called a totally normal neighborhood, which means a neighborhood such that any 2 points in that neighborhood can be joined by a unique minimizing geodesic, but that minimizing geodesic doesn't have to stay in that neighborhood. It's really annoying that that happens, right? And then next class, we're going to improve it even more by saying we can find what's called a totally geodesic neighborhood. No, sorry, geodesically convex neighborhood. Okay, so before we remind ourselves what the Gauss lemma was, let me make a definition. Let V be an open neighborhood of the zero vector in TPM such that exp P is a diffeomorphism onto its image. Diffeomorphism. So we've seen that such a V always exists. Such a V always exists, and that's because, let me remind you, the exponential map has some open domain on which it's a smooth map, and we computed the push forward at the identity, the push forward at the origin, and that was invertible. In fact, it was the identity map, and therefore by the inverse function theorem, by shrinking the domain possibly of the exponential map, we can ensure that it's a diffeomorphism onto its image. Okay, so then the image U is an open neighborhood of M called, of P, open neighborhood of P in M called a normal neighborhood. Normal is one of the most overused words in all of mathematics. I think only Euler is more overused than normal. So you just have to remember when you see the word normal, what it means in each context. So, so what do we know about this? Here's V. This is the origin. This is V, and the exponential map takes us to U, which is the neighborhood of P. Well, any point in U, let's call it Q, it's going to be in the image of some, it's going to, because of this is a diffeomorphism, there's going to be a unique point V in here, in capital V, which is a subset of TPM, such that Q is XP of V. But remember, this is gamma V of 1. Okay, so it says that if we take the geodesic starting at P with initial velocity V, this is TPM. If we take the geodesic with initial vector little v, then we can follow that geodesic for time 1 and we get to the point Q. So in other words, any point in this normal neighborhood is connected. So for any point in U, there exists a geodesic from P to Q. Okay, so for any Q in U, there exists a geodesic from P to Q. What we're going to do is show that by possibly shrinking U even further, that this geodesic has some nice properties. But before we get there, let's make some more definitions. Suppose that B epsilon 0 bar is contained in V. What is this? This is the set of all W or little v in TPM such that the norm of V is less than or equal to epsilon. So this TPM is just a vector space, and it has an inner product on it, which is the inner product given from the metric on the manifold. Okay, so whenever I talk about norms in TPM, it's always with respect to GP. So suppose this is in here, then its image is contained in U, is called a geodesic ball, or also called a normal ball. It's a normal neighborhood because it's contained in a normal neighborhood, and it's a ball because it's the image of a ball, right? It doesn't make sense to talk about balls in M. It doesn't make sense in a normed vector space. It's called a geodesic ball or a normal ball centered at P with radius epsilon. Okay, so what does this mean? What is the radius? You know, right now, all it means is that it's the image under the exponential map of some closed ball of radius epsilon in V using the norm GP, where we assume that this closed ball is contained in the set in the open neighborhood of the origin, where the exponential map is a diffeomorphism. So we often write B sorry, I don't want this closure here. I want the closure to be in here, but I wanted to call this the geodesic ball. We write B epsilon of P for X P B epsilon 0. Okay, so I look at the points in capital V whose distance from the origin is less than epsilon, and I map those under the exponential map to some subset of U. It's going to be an open subset. This is an open neighborhood of P, because this is open in TPM, and the exponential map is diffeomorphism, so it's a homeomorphism. I wanted to say one other thing here. Oh, and then XP of the boundary of this ball. So this here is the set of all points V in TPM such that the norm of V is equal to epsilon. This is called a geodesic sphere centered at P with radius epsilon. And this is why I wanted the closed ball to be in V, right? Because I want to be able to map the boundary. The boundary is part of the closed ball. I want to be able to map that into M by the exponential map homeomorphically. So again, if this is V, and then U is the image under the exponential map, actually, let me just draw this pink thing, just the boundary is there. And then actually let's do this one is the closed ball, and the image of the open ball is, so this open pink set here is BP epsilon. So we're only going to talk about geodesic balls and geodesic spheres if the radius is such that the closed one, where am I? The closed one is contained in the domain, in the set where the exponential map is a diffeomorphism. Yep.
If I remember well, I think you mentioned before that we're going to define a
Yes, yeah. Yes, yeah, they are. Yeah, yeah. Well, what's going to happen is that the metric. Sorry, the question was.
Yeah.
Yes, I will repeat the question. Thank you. We will at some point in a few weeks show that if you have a Riemannian manifold, it induces a metric in the sense of metric spaces, and therefore you get a topology from that metric space metric. It's too bad that's the same word metric in both cases, right? So from the metric space metric, we get a topology, and that topology coincides with the original topology. And you can see that these geodesic spheres form a basis for this topology, and they're gonna form a basis for the other topology as well. So there's only one topology. Yeah. You can't get new topologies from Riemannian metrics. Okay. So the next thing to show, we'll show that geodesics, are locally length minimizing. In a precise sense, which I'm going to say in about a minute. So if a geodesic if 2 points are close enough in some sense, if they're in a particular open neighborhood of 1 point, then there will be a geodesic joining P to Q, and that will be a minimizing curve from P to Q. We're going to prove that in a minute. But let me remind you, because we're going to need it. So recall the Gauss lemma. We proved this last time, and rather than give a formal restatement of the lemma, let me tell you what it means in terms of this picture. So the Gauss lemma says, I'm going to draw the same picture again. So this is B epsilon 0 closure. All of this is happening in TPM. Sorry, the origin is in here. This is TPM. And here's our manifold M. This, I need another color. This is inside the domain of where the exponential map is diffeomorphism. And this gets sent to some neighborhood of P. So the Gauss lemma says, well, we know that the rays, the straight lines emanating from the origin, as long as they stay in this blue set, are map, or not even in the blue set, in the domain of the exponential map, are sent to geodesics emanating from P. So these orange lines are geodesics emanating from P. And what we proved with the Gauss lemma was that if you took a vector in this blue set in TPM, which was tangent to the ball, right, the unit sphere, or not the unit sphere, the sphere of radius epsilon. If you have a tangent vector to this sphere inside this vector space, then under the exponential map, this gets sent to some vector tangent to this pink set, and this geodesic has a velocity here. It says that this angle, which is 90 degrees here, is also 90 degrees here. Okay, so it says that the geodesics that emanate from P are intersect the geodesic spheres at orthogonally. So maybe I'll write that on the other side of the board. Right, it said a little bit more than that, but this is really the content that we're going to need today. In particular, you know, the push forward of the exponential map. So this is a diffeomorphism. So right, this blue manifold is identified with this blue manifold. They're diffeomorphic, and so it'll take tangent vectors to submanifolds to tangent vectors to submanifolds. So this green vector is tangent to this submanifold. It'll go to this green vector tangent to this submanifold, and this curve has a tangent vector. It'll go to a tangent vector to this curve. So the push forward of xp at this point will map the tangent space here isomorphically onto the tangent space here. And there's a metric here from GP, and there's a metric here from G at this point. And this map, the push forward, does not have to be in isometry, but it does preserve the angle between the radial lines and vectors which are tangent to the sphere. It preserves those. It might not, if I have two vectors tangent to the sphere, they're going to get mapped to vectors tangent to the sphere, but that angle doesn't have to be in isometry there. It only preserves the orthogonality here. That's what we proved last time. Okay. So now that we've reminded ourselves what the Gauss lemma says, let's prove the following proposition. Let P be an M. Let U containing P be a normal neighborhood of P. That just means it's the image. We have it here, right? It's the image of an open neighborhood of the origin in TPM on which the exponential map is a diffeomorphism. Let B contained in U be a geodesic ball centered at P. I think I want such that, so B is xp of some B epsilon 0. And we want, I think we want, it will come clear in the proof, that the closure is also contained in xp inverse of U. Okay, so I want exactly this situation. I want where I can actually talk about the geodesic sphere is in U. So the geodesic sphere boundary of B is in U. Okay. Yep. Oh, it did. I can't remember what I said. Let's see. Yeah. You're right. So good.
Can you repeat that question?
Yes, I will. So everything I just wrote down here is superfluous because this was implied in my definition of geodesic ball. I only defined geodesic ball in the case when the closure of this, the closed ball, was also contained in the domain of xp on which it's a diffeomorphism. Okay, so the boundary of this set, which is equal to the image of the boundary because it's a homeomorphism, this is also contained in U. Okay, this is the geodesic sphere. Right. So every time we talk about a geodesic ball, it means its boundary is also in our normal neighborhood. So I'm still stating the proposition. Let gamma from 0, 1 to B be a geodesic segment with gamma of 0 equals P. So what is a geodesic segment? It means you take a geodesic, the geodesics have a maximal domain of definition, which is some open interval, which could be the whole reals. And I'm just restricting it to some closed bounded interval. So it's just a restriction of a geodesic to a closed bounded interval, which passes through the initial point P. And the big fact here is this. So gamma, the image of gamma lies in the geodesic ball B. So in the picture, again, if I draw B epsilon 0 here, it's going to get mapped to what I call B epsilon P. And it starts here. We know that the geodesics that emanate from P when you look at them under the inverse of the exponential map, they correspond to rays emanating from the origin. So this is gamma here. And it stays in this ball. Still stating the proposition. So if alpha from 0, 1 to m is any piecewise smooth curve from gamma 0 to gamma 1. So note, alpha need not stay in B. Then the length of gamma is less than or equal to the length of alpha. Moreover, so gamma is a minimizing curve between its endpoints.
Could the camera pan, please?
Oh, the camera has to. Oh, Sydney. Sorry, move the camera. So gamma is a minimizing curve between its endpoints. And moreover, equality holds if equality holds here in star if and only if alpha is a reparametrization of gamma. Orientation, well, doesn't matter. No, orientation preserving reparametrization of gamma. So certainly we know the length is independent of reparametrization. So if I reparametrize gamma, then it's still going to have the same length, but it may not be a geodesic anymore, right? And it won't be in general. We know that if you want to reparametrize and we want to keep the interval to be 0, 1, right? Then that means we're not shifting we're not translating the parameter. And so the only thing we can do if we wanted to keep it to be a geodesic would be to do a constant speed reparametrization. But in general, if it's a reparametrization that's not constant speed, it definitely won't be a geodesic anymore, but it'll have the same length. So this is the best we can hope for. So what does it say? It says, let's go back to this picture. It says that, so here's gamma, P is gamma of 0. This thing is gamma of 1. It says that if I take any other curve, piecewise smooth curve joining these 2 points, even if it doesn't stay in B, the length of this will be at least as big as gamma. So for any 2 points in this normal neighborhood, sorry, if I take P as one of the points, if I take any other point in this geodesic ball, we know there's a geodesic connecting P to that point, and this proposition says it's minimizing. Okay, so before we prove it, let's summarize that. So the proposition says if Q is in B epsilon P, then there exists a unique minimizing curve, minimizing geodesic from P to Q. Okay, so really what I should be saying, there exists a minimizing curve because this thing says gamma is minimizing, and it's unique. The curves, the minimizing curves, what does it mean to have a minimizing curve? It means that the length is less or equal to the length of any other curve going between those 2 points. That's independent of reparametrization. So this thing tells us if we had any other curve from P to Q, even if it doesn't stay in B, then the only way you get equality here is if they're the same up to reparametrization. And that's where we get the uniqueness. Okay, so in a geodesic ball that has a center, every geodesic ball has a center. Every other point in that geodesic ball there does exist a minimizing curve from P to that other point, and it's a geodesic, right? There was no reason a priori that a minimizing curve had to be a geodesic. We'll prove later today that all minimizing curves are geodesics, right? But right now we're saying we know there's a geodesic from P to Q because that's what it means to be in a normal neighborhood of P. There's a geodesic from P to Q. That geodesic is minimizing, and it's the only, up to reparameterization, minimizing curve from P to Q. Okay? So that's what we're going to prove. Proof. So without loss of generality, since length is independent of reparametrization, we can assume alpha is a constant speed parametrization. In other words, alpha prime of t constant. Why can I do that? Well, I know I can reparameterize by arc length for any curve. And then if I reparameterized it by arc length, it would go from 0 to L, where L is the length. But I want it to go from 0 to 1. So I just rescale. If I rescale the parameter for a constant speed, for a unit speed parameterization, then it's still constant speed parameterization. And I can make the domain 0 to 1. In particular, this says that alpha prime of t is not equal to 0 for all t. So strictly speaking here, I'm being a little sloppy because it's piecewise smooth. So alpha prime doesn't have to be defined. It could have two values at a finite number of points, a left limit from below and a limit from above, but they're both non-zero, right? Alpha prime is never 0, even when it has two values. Okay, so let's start the proof. Okay, so proof. So first, suppose that the image of alpha lies inside B. And then we'll consider the case where it exits B. So since XP is a diffeomorphism onto B, well, before I say that, so we know XP is a diffeomorphism onto B. Let's suppose that for all t bigger than 0, alpha of t is not equal to P, i.e. alpha never returns to its starting point. We can assume that because if it did at some point get back to P, then we can just consider the curve from the last time it got to P, and we're going to prove that the length after that is already bigger than the length of gamma, and the part we threw away has positive length, right? So if not, ignore the interval 0 T1, where T1 is the last time such that gamma of T1 equals P, since that since gamma restrict alpha, since the length of alpha is going to be at least as big as the length of alpha restricted to T1, 1. Yes, thank you. So if I can show that this is already bigger than the length of gamma, then certainly this will be bigger than the length of gamma. Okay, so hence, now I'm going to use the fact that this is a diffeomorphism. For all t positive, for all t in 0, 1, open 0, closed 1, we can write alpha of t as, well, we know it's going to be x of something because we're assuming alpha always lies in B, okay? And if we go back and we look at our picture, so this is xp inverse of B, which is an open ball centered at the origin of some radius in TPM. So as long as we're not at the origin, there's a unique unit vector. If I take any point here which is not at the origin, and remember the origin corresponds to P, and other points in here correspond to points other than P, because this is a bijection. So as long as we're not at the origin, any point here corresponds to a unique unit vector and a distance, right? I'm saying that all the points in a vector space, a norm vector space other than their origin, are uniquely described by the unit vector to that point and the length of that the vector to that point. So we can write alpha t as xp of r of t v of t, where v of t is a unit vector where, well, first of all, r from 0 to 1 to the reals is a positive smooth function, piecewise smooth function. And t goes to v of t is a piecewise smooth curve in TPM such that v of t has length 1 for all t. Okay, so that's exactly what I'm saying here. We're assuming it never comes back to P. It's only at P when time is 0. So after that, it's somewhere in this ball, but it's not at the origin. So therefore, it has some unique unit vector in that direction and a positive length. Okay, so we can write our curve like this. So there's two ways in which it has dependence on time, on t, right? Because r depends on t and v depends on t. I'm going to explicitly sort of separate the two t dependencies and saying that there's a dependence on t through the dependence on r, because that's a real variable too. And then there's more dependence on t, which comes from v. But I'm not going to denote that any other way. So I'm going to write alpha of t is sigma of r of t, t. So this is the dependence on t from r, and this is the dependence, the rest of it, the dependence on t from v. It's just going to be more convenient to not think of that separately because I don't want to think about trying to differentiate with respect to v. What that means, we're not going to have to do that. Okay, so and these are piecewise smooth, of course, because alpha is piecewise smooth. Yeah. No. Here? Well, you could, but you'll see now. So the question was, why do we have two functions and not just one? It's true that this thing is some curve in this set, which depends on t, which never goes through the origin after time 0. But I want to separate it into its length and its direction because I want to use the Gauss lemma. Okay, so you'll see the answer to that now. Okay. So hence, except at a finite number of points where the velocity can jump, everywhere else we have alpha prime of t. Well, I can differentiate with respect to r and then differentiate r as a function of t, or I can differentiate the other dependence on t that doesn't come from r, right? So This is a little bit sloppy notation, but we know what it means. It means that this is thinking of this t in here as being constant and then differentiating the v of t. Okay. And what is, yeah. It's just xp of r of t, v of t. It's a smooth function of t, right? But I'm going to write it as, well, it's a smooth function of r of t and the rest of the dependence on t. Okay, so if you want, you can make this more precise, but it's going to introduce a lot of notation that is going to be a waste of time, because you can see it's not going to matter. Right? Well, we're going to use the Gauss lemma, and we use the symmetry lemma to prove the Gauss lemma. Okay. So what is sigma of t? D sigma dt. D sigma dt is the velocity vector field. If I do this at some t naught, right? This is the velocity vector field of the curve. T goes to x p r of t naught v of t at t equals to t naught. Okay, so this is the part where we think of this as being constant and just vary the t here. Okay, so what is this? That is a unit vector. So this is a curve. This is a curve on the geodesic sphere. Boundary of B, because this guy here, R of T naught V of T, the ball on a geodesic sphere, right? Because this thing has constant length. It has length equal to R of T naught, which is some positive number. So this is a curve. Before I apply the exponential map, it's a curve on a sphere of constant radius centered at the origin, and therefore under the image by the exponential map, that'll be a geodesic sphere. So by the Gauss lemma, this is orthogonal to d sigma dr, because d sigma dr is the velocity vector field of, let's say at t naught well, let me not put too much notation, of r goes to xp rv. Okay, so here I'm thinking of this as a function of r, and I'm setting that thing to be a constant. So the way to do this more carefully would be to introduce an s and a t, and to think of them as independent, and then eventually let s equal to t. But this is kind of harmless. So if I fix this, and I just think of this as a function of r, then d sigma dr is just, that's a fixed unit vector, and I'm doing xpr of a unit vector. So that's exactly a unit speed geodesic. This is a anyway, this is a geodesic, which is a radial geodesic emanating from P. Okay, so let's see if we understand what's happening in here. Alpha is a curve in the manifold. So this is a tangent vector somewhere to the manifold. That's a scalar, because r is a smooth positive function of t. So this is just a real number. These two are tangent vectors. And the Gauss lemma tells me. Question?
Camera's not, you're not in the frame.
Sorry. So the Gauss lemma says that these two vectors are orthogonal. Okay, because one is is a tangent vector to a radial geodesic, and a geodesic emanating from P. And the other one is a tangent vector to a curve which lies on a geodesic sphere. Okay, that's exactly what the Gauss lemma says. Those things are orthogonal. So now, also, so we have the d sigma dr and d sigma dt, sorry, d sigma dt are orthogonal. And also, since v of t is always length 1, d sigma dr is 1, because d sigma dr is the velocity of this geodesic. Okay, it's r maps to x r of v. That's a unit vector. So this is a unit speed geodesic. Unit speed geodesic emanating from P. So I know that these two guys are orthogonal, and this one has length 1. So if I take the norm of that equation, it's going to be the sum of the squares of the norms. So hence, alpha prime t norm squared is equal to r prime of t squared plus d sigma dt squared. That's because they're orthogonal, so there's no cross term, and this thing has length 1, so that's why I get this. Okay. Now, let's integrate this inequality. So this is greater than or equal to r prime of t squared, because this is non-negative. So let's integrate epsilon to 1 alpha prime of t dt. That's going to be greater than or equal. If I take square roots here, that's going to be greater than or equal to epsilon to 1 r prime of t dt. And that's going to be greater than or equal to epsilon to 1 r prime of t dt without the absolute value. Okay, this is going to be inequality 1, and this is going to be inequality 2. And here, of course, we can do this by the fundamental theorem of calculus. This is just r of 1 minus r of epsilon. Okay, so now let's look a little more closely at r of 1. Gamma of 1 is equal to alpha of 1. Remember, our hypothesis was that alpha was another curve from P to Q with the same final point. And by our expression for alpha, this is xp r of 1 v of 1. Okay, so here's the picture. This is gamma of 1, which is xp r of 1 v of 1. And this is a unit vector. Okay, so the length of gamma is exactly r of 1. Remember, we talked about this last class. If you have a unit vector here, then x of some positive number times a unit vector, if you vary this positive number from 0 to some let's say s, then that's going to give you a curve, a geodesic emanating from P, whose length, because that's a unit vector, is s. Okay, so the length of gamma is exactly this positive number here. So what do we have? We have that epsilon to 1 alpha prime of t dt is greater than or equal to r of 1, we said, is the length of gamma, minus r of epsilon. Now let epsilon go to 0. This, of course, becomes the length of alpha by continuity, and r of epsilon goes to 0, right? Because as epsilon goes to 0, the point, the value of r at the origin is 0, right? It's like spherical coordinates in TPM. So this is L of gamma. So we've shown that if alpha lies entirely in B, its length has to be at least the length of gamma. Okay. What we're going to do now is show that if equality occurs, alpha is a reparametrization of gamma. And then we're going to show that if alpha doesn't lie entirely in B, this is never an equality. It's always strictly positive. Yeah. Because R is not defined at 0. Yeah, the limit is epsilon goes to 0, R of epsilon is 0. That's right. Yeah. Okay. All right, so now suppose equality holds. Okay, so that means we have equality in 1 and 2, right? Because I have 2 inequalities. So if we have equality here, well, what's going to happen here? These are 2 integrals over the same interval of non-negative functions, right? The only way we'll have equality here, these are continuous. These functions are continuous except for a finite number of points. So except for those discontinuity points, that means this will have equality here. That means this d sigma dt will be 0 for equality in 1. So equality here, equality in 1 tells us that d sigma dt equals 0. So v of t is constant. Remember, d sigma dt was basically the dependence on alpha through v of t. Okay, so that means that sigma alpha of t is sigma of r of t times v, which is constant, which is just x p r of t v. Okay, and equality in 2. Well, let's look at that one. Here you have to work a little bit harder. It's supposed to have equality here. This is non-negative because it's an integral of a non-negative function. So if they're equal, that means this has to be non-negative, so it's equal to its absolute value. That means I have equality in the theorem that says that the absolute value of the integral is less than or equal to the integral of the absolute value. And there's a mean value theorem for integrals, which says the only way that happens is if there's at least one point, one time at which the value of this function at that time is equal to this thing, some average value of this. Right? I can't remember exactly the statement of the mean value theorem, but basically equality here will force this thing to be positive at least one point. Sorry, it will force this to be non-negative everywhere. And then because we're assuming constant speed parameterization, it's going to be positive. So I'll leave this as a details for you. The mean value theorem for integrals forces r prime of t equals r prime of t for all t, where this makes sense, right? Except for the finite number of t's. So this means that r prime of t is non-negative, but I still have it here from this, but alpha prime of t is exactly r prime of t is positive because we had constant speed parameterization. So r of t is positive for all t, and this says that alpha is a reparametrization of gamma, right? Because gamma is exactly what I would get if I just put a t here. Gamma of t is xp of tv, and this is just a reparametrization. Okay, so what have we done? We've proved that when alpha stays in B, its length is at least as big as the length of gamma. And the only way we get equality is if one is a reparametrization of the other. So it remains to show, yes? Yes. No. Yes. Yeah. So now I have equality here for every epsilon, right? No. Sorry, you're right. I have equality in the limit. So these functions are well defined everywhere. Well, they're discontinuous at a finite number of points, and they don't make sense at zero, but that doesn't affect the integrals. Right. Good. So it remains to consider the case when alpha does not stay in B. Okay. So let's let T1 be the first time such that alpha of T1 is in the boundary. Okay, because the image is it's a continuous function. So the only way it's going to go from inside B to the exterior of B is if it passes through the boundary. And let's let rho be the radius of B. So in other words, B is x p of B rho 0. Then let's look at the length of alpha in this case. The length of alpha is strictly bigger than the length of alpha restricted to 0 T1. And this is because T1 is between 0 and 1. Okay, so I'm integrating the speed, which is a positive constant, over some interval, which is going to first include 0. It's going to go from 0 to T1 and then T1 to 1. So it's going to be bigger than this. But this is at least rho by the first part of the proof. That's why we have to do that case first, because this guy completely lies in B. And this is less than or equal to, is greater than or equal to the length of gamma. Sorry, what am I doing here? Let me draw a picture. So we start here. Alpha comes out at some point. This is alpha of T1. And this distance here is rho. This is the picture in the TPM. So I'm saying that this is a curve. This blue part here is a curve from here to here. So by the first part of the proposition, this is going to have length at least equal to the length of the geodesic from here to here, which has length rho. And gamma, alpha comes back eventually because the endpoint alpha of 1, which is gamma of 1, is in here. So that's that length. This is gamma. This has length less than or equal to rho. Okay. So in the case when alpha leaves B, you always have a strict inequality. In this case. So the only thing that's bugging me here a little bit is that I'm saying I'm applying this proof to this ball. Yeah, but I proved it for whenever a curve lies inside a geodesic ball, right? So you can always find a larger geodesic ball, open geodesic ball containing this closed geodesic ball, and apply the first part to it there. That's why, because this guy actually ends up on the boundary. So by the first part of the proof, applied to a slightly larger ball. Geodesic ball. Okay. So that was fun. I want to make some remarks before we go to the next result, but are there any questions?
Yeah, I have a question. So
good.
Often you just define a geodesic as a minimizing curve and you work out the differential equations and calculus of variation. So
Yep.
This is a different approach, different proof.
Yeah, we're
So,
going to get to the variational point of view near the end of the course. But yes, we're going to, one way to, so the question was, what does this have to do with the usual approach to geodesics as critical points of the length functional, right? So this is chapter 9 of De Carmo. We're gonna study the length functional and the energy functional for curves, look at the critical points and see that we get geodesics. And that's another way to prove that a minimizing curve is a geodesic. That's the next thing we're going to do, right? If you had a minimizing curve, it must be a geodesic. We haven't proved that. What we proved is that if you have a geodesic, as long as you take a small enough piece of it, it's minimizing. Okay, so if you know that geodesics are critical points for the length functional, then if you had a minimum for the length functional, that certainly is a critical point. So it has to be a geodesic. But we're going to get to that in maybe the last 4 weeks of the course. Okay. So let me make some remarks. We've shown that for all Q in B, there exists a unique minimizing curve from P to Q, and it is the radial geodesic from P to Q. That just means that on the in the normal coordinates given by the exponential map, it's the radial line from the origin to the vector v, so that gamma v of 1 is Q. But I want to make another remark. So we don't know that if Q1 and Q2 are in B, where neither equals P, whether we don't know if Q1 and Q2 are in B, but neither of them is P, whether or not there exists a minimizing curve between them. Okay, so this actually is not always true, but it will be true if we make the neighborhood even smaller. So next time, this will be true if we take a smaller neighborhood. In fact, we probably won't get to it today. Maybe I'll get the statement, but I don't think I'll finish the proof. So I wanted to make, so those are the two remarks. I also want to emphasize that this result is local and it can't be global. So note the previous proposition is local and it cannot be global. In other words, there are examples, right, where if you make your geodesic too long, it's no longer a minimizing curve between 2 points. And here's the standard example. If I look at the sphere, then you're going to show on the homework that the geodesics on the sphere are exactly the great circles. Okay, so now suppose I take this point and I want to look at a geodesic ball. What does that mean? I want to follow the geodesics emanating from this point up to some finite distance, which will be the radius of the ball. So if you take great circles coming out of the North Pole, and you follow them for the same distance, you're going to get this cap, this sort of polar ice cap here. That's a geodesic. The interior here, the blue part, the inside the pink dotted line is a geodesic ball, and the pink line is going to be a geodesic sphere, which is an equator. Okay, and what's true then is if I take any point, if this is a geodesic ball, right? If I take any point inside this geodesic ball, then the radial geodesic, the one that goes from the North Pole to here, is a minimizing curve from here to here. Okay, but what happens now if I try to make the radius of this geodesic ball too big? If I allow my geodesics to have longer and longer length, even when I get to somewhere here, let's say the length is just less than pi, because if I went all the way to the South Pole, it would have length pi for radius 1. Suppose the length is just less than pi, that's still true. If I think of this huge geodesic ball, right? I'm just omitting basically a neighborhood of the South Pole, an equator near the South Pole. It's still going to be true that if I take any point in that geodesic ball, there's going to be a unique geodesic emanating from here going through here, and that's going to be the minimal length curve from here to here. But now if I suddenly go up to pi, bad things happen. First of all, the exponential map ceases to be a diffeomorphism if I allow the length to be pi, because it's no longer one-to-one. All these geodesics, when you follow it by length pi, you're going to end up here. Okay, so already you can see the exponential map can't be a diffeomorphism everywhere in general. It's going to eventually cease to be a diffeomorphism. But you can also see that if I took this geodesic, this great circle, and I went around to the other side, you can see that this curve is not the minimal length curve joining these 2 points, because the minimal length one is on the other side. Okay, so this proposition cannot be globalized in general. Okay, there's 2 problems that can happen. First of all, the exponential map will cease to be a diffeomorphism in general after some radius. Here, everything is nice and symmetric, right? So it really does fail in all directions at the same time, right? But in general, depending on the direction you're moving on, there'll be some distance where you hit a problem. We're going to start to see that. It's going to be called conjugate points. And then, of course, even independent of that, you could have curves which are geodesics, which are not the minimal length curve between 2 points. You can see this case when you take points, there's always going to be, well, another thing that can go wrong, if you took the North Pole and the South Pole, now there's infinitely many minimal length curves between them, because any of these arcs, these meridians, lines of longitude, are geodesics, and they all have the same length, right? So eventually you lose the uniqueness. You might have more than one geodesic joining 2 points. And also, it's not true that any geodesic is always minimizing between 2 points, because as I said, that orange one is a geodesic from here to here, but it's not minimizing because the green one is shorter. Okay, yep. We're going to see that can't really happen in some sense. Right? Yeah. So it's going to be related to compactness and well, I mean, if you want to,
Could you repeat the question?
Create problems. Oh, sorry. The question was, can you give an example where this kind of thing happens where the manifold is not closed? And I guess you mean compact when you say that. So we'll see that if you have a non-compact manifold, really the way to create pathological things is to pull points out of it to make it, or here too, if you pull points out, you can create issues where geodesics fail to exist, or bad things happen by sort of cheating and pulling points out. But if you have something which is complete, we're going to see that if well, I don't want to get ahead of myself, but we're going to see if it's complete and it's sort of positively curved in some sense, it has to be compact. And if it's negatively curved in some sense, then the manifold has to be complete. I can't remember exactly the statement. So all these answers to the question are coming in like week 6 and 7 and 8, but I can't remember exactly the statement right now. So I'll ask you to just be patient. Okay. Okay, so what have we done? We've shown, so remark is here, we've shown that if you take a geodesic ball, then for any point centered at P, then for any Q in B, there exists, we know there exists geodesic from P to Q, and this curve minimizes, and it's the unique minimizing curve from P to Q. Okay. Now, what we want to show next, we'll show that any minimizing curve between 2 points must be a geodesic. So note, there need not exist a minimizing curve between 2 points. There need not exist a minimizing curve between 2 points. I already gave you an example of that last time. So that's going to be a question which is going to be related to completeness, right, in a few weeks. But suppose there was a minimizing curve between 2 points. We're going to show that it has to be a geodesic. So in particular, and this is piecewise smooth. Remember, I defined last time what it means to have a minimizing curve, and our class of curves are the piecewise smooth curves. So in particular, if we have a piecewise smooth curve between P and Q, and its length is no greater than the length of any other curve from P to Q, piecewise smooth curve from P to Q, then that curve is a geodesic. So in particular, it's smooth. Okay, it's not just piecewise smooth. So I have 13 minutes. We can't get there yet. So let's see what I can do in 13 minutes. So first, we need another technical result. Hopefully a little less painful than the first one. So we'll show that any P in M has an open neighborhood W such that W is a normal neighborhood of each of its points. What we've shown so far is that every point lies in a normal neighborhood. Okay, but it's more to ask for that normal neighborhood to the same set, the same open set, to be a normal neighborhood of every one of its points. So this is called a totally normal neighborhood. Or a uniformly normal neighborhood. Okay, so no. Well, you get normal coordinates are different, right? Remember, for a normal neighborhood. So the question was, does this mean the Christoffel symbols vanish everywhere in W? No, it's not, because to get a normal coordinate system, it has to be centered at a point. You have to choose an orthonormal basis for the tangent space at that point. Okay, so you can use W. Well, so what am I saying here is that this is the manifold. If I have a totally normal neighborhood W, then if I chose some point P in here, then the inverse image, this is XP inverse of W, and this is in TPM. But if I chose some point Q in here, then I would get XQ inverse of W, and this would be in TQM. Okay, so each one of these gives me a different coordinate chart. So in both cases, I also have to choose an orthonormal basis of TPM or TQM to get coordinate chart. So in this coordinate chart, the Christoffel symbols would vanish at P. In this coordinate chart, the Christoffel symbols would vanish at Q. Okay. So let's see. I'm in this awkward situation where I don't really have time to do it, but it's too much time to stop. There's no way I can do 2.5 pages in 10 minutes. Maybe I could. Theorem. For all P and M, there exists W containing P open and a delta positive such that for all Q in W, XQ is a diffeomorphism from on B delta 0 TQM, whose image XQ of B delta 0, which is B delta Q, contains W. Okay, so in other words, I can choose a neighborhood of, if I fix a point, I can choose a neighborhood of that point and some positive number delta, such that for every point in here, this is contained in the geodesic ball of radius delta centered at Q. Okay, so W is a normal neighborhood of each of its points, because W is contained in XQ of B delta 0, which is B delta Q for all Q in W. Okay, that's a normal neighborhood of Q. So any open neighborhood of Q contained in this normal neighborhood is a normal neighborhood. All right. Yeah. No. It just means that we can choose the same delta that works for every point. Yeah. Lee calls it uniformly normal. Del Carmo calls it totally normal. Both words are bad. Okay, so maybe what I'll do is I'll just start the first half of the proof to motivate why we're doing what we're doing, and we'll have to continue on Monday. Okay, so proof. So recall there exists some U containing P open and an epsilon positive such that if Q is in U and V is in TQM with norm of V less than epsilon, then X Q of V is defined. Right, basically this is coming from the ODE theorem that we can choose an open set in the set of initial conditions on which we have uniform time existence for the solution, and then by the rescaling lemma we can make that one. So we talked about that a couple of lectures ago. And we have U tilde is the set of all QV in the tangent bundle such that Q is in U and V is in TQM with V less than epsilon, norm of V less than epsilon. This is open in TM. This is exactly the notation we had 2 lectures ago. Let's define a map capital F from U tilde to M times M given by F of QV is exactly Q and then X Q of V. Okay, so basically this is a map which takes a point in here, and it gives you 2 points in M. The first one is always this point, and the second one is what you get by taking the geodesic, starting at Q with initial velocity V, and following it for time 1. Okay, this F is smooth because the component functions are smooth. right? I have a map into a product of two manifolds. So it's going to be smooth if and only if the projection onto each factor is smooth. But what's the projection onto the first factor? It's just the restriction to U tilde of the projection map on the tangent bundle. It takes Q comma V to Q. And then, of course, we know the exponential map is smooth on this set U tilde. So I have a smooth map. And the motivation for this map, I'm going to stop in 3 minutes. The motivation is that a point is in the image of F if there exists a geodesic. It's not if and only if, but if there exists a geodesic from Q to it. Right? So this guy is another point in M, and there's a geodesic from Q to that point because it's in the image of the exponential map. Okay, so the idea now is to want to show that F is a diffeomorphism. It's not, but if we shrink the domain, it will be. So the idea is to show that if we shrink the domain U tilde of F, then we get a diffeomorphism. And it's not immediately obvious why that gives it to us, but we'll see it from there. So maybe I just want to write down one more line and we'll start from there on Monday. So notice that where does F take P comma 0? Well, P comma 0 is going to be sent to P and then X P of 0. We follow the geodesic with initial velocity 0 starting at P for time 1. That's a constant geodesic. So this is P, P. So hence, the push forward of F at P0 is going to go, it's going to be a linear map from T P0 of U tilde to T PP of M. Okay, of M times M. But this guy, U tilde, you can make U small enough so it's, for example, a domain of a coordinate chart. In other words, the tangent bundle restricted to U will be diffeomorphic to U times Rn. It'll be a product. It'll be trivial. And therefore, we're going to get that this is identified with TPM plus TPM. And this one too, you know that the tangent space of a product is the direct sum of the tangent spaces. Okay, and this is a linear map. So I probably should stop here, even though I have 2 minutes, I can't really do this calculation. So we're going to compute the push forward, right? Last time we did something like this a few lectures ago, we got the identity, and you think you might get the identity again because there's some identifications happening here, right? But these are really, the same space on both sides. We're not going to get the identity, but we're going to get something that's clearly invertible. And then it's going to follow that as long as we, by the inverse function theorem, as long as we shrink the domain, we get a diffeomorphism, and from there we'll be able to finish the proof. So we'll finish the proof next time. I'll restate the theorem. Probably what I'll try to do is write all of this again to begin with, because we already discussed it, and go from here. So we're about a third of the way through the proof. And then, so that'll take us, so next time, also from this, we'll show that any minimizing curve is a geodesic. And then we'll prove existence of geodesically convex neighborhoods. So none of this is going to be obvious yet, but let me just say the first step when we had normal neighborhoods, we saw that if you had any other point in the normal neighborhood, there was a geodesic from here to here. And it was minimizing, and it was the unique minimizing curve. One consequence of this totally normal neighborhood theorem, which is not obvious yet, but if W is a totally normal neighborhood, then for any 2 points in here, there's going to exist a unique minimizing geodesic between them. The problem is that geodesic doesn't have to stay in W, which is annoying. And the geodesically convex is exactly going to fix that. It's going to say that if you have any 2 points in here, there's a geodesic between them, unique minimizing geodesic, and it stays in there. Okay, so we're building our way. We're in the middle of this construction now. We've done this. We'll finish this on Monday, and then we'll do this. And then we'll be done with chapter 3. We'll move on to curvature, which is going to be a lot less technical, and also, I hope, review. And then when we get to Jacobi fields, we're gonna merge the two, curvature and geodesics, and see how they're related. Okay, sorry, I went 2 minutes over. So that's it for today.